This is Dick Moberg, and I've risen from the dead to host this webinar. Normally it's been Ethan and Craig's on a plane, and Ethan's here, but I figured I'd do it. So welcome to our webinar, and thanks for tuning in. So I think you know why we're doing these. We're building this platform to allow you to manipulate and manage data in neurocritical care. And this webinar is part of the series of tools that we provide. So these are tutorials, cases and examples, and so forth. We keep talking about starter grants, and we do plan to do that. We've had a lot of travel the last early months of the year, but we hope to start those by April, and we'll be announcing that in our newsletter, the Neuroscience Monitor. So stay tuned. So for we'd love to get your feedback on the webinars. Let us know if there are other topics. If you'd like to present one, we'd love to have you. Probably the best way is to email Craig at moberganalytics.com and give him your suggestions. Thank you. The past webinars the recordings of those are on our website. Just go to the website and look at webinars, videos, and you'll see what we did prior to this one. And probably not for this webinar, but for prior webinars, we actually had assets, data, and some instructions on how to download that. So look at that. That's on our website as well. We have our webinars on the third Friday of the month at 1 p.m. Eastern time. So far, the next 3 slots are open if you'd like to do one. We have some people that are going to be filling those, but we don't know exactly which month yet. Since it's a Zoom webinar, to post questions, access the Zoom Q&A feature located in the Zoom menu. I think most of you know how to do this by now. And this is being recorded and will be available shortly on our website. So today, I know it's no secret because you just heard Eddie talking, but we're very excited to welcome Dr. Eddie Amorim. He's been a longtime collaborator and friend of the company since he first came to UCSF. He's also been incredibly gracious with feedback and testing as we subjected him to early, which means buggy versions of our code. And we love working with him. Eddie completed medical school in Brazil and did his residency at the University of Pittsburgh. He completed 3 fellowships, so neurocritical care at Harvard Mass General, Neurophysiology, Epilepsy at Mass General, and he did a postdoc fellowship in neuroscience and machine learning at Harvard MIT. Currently, he runs the Amorim lab at UCSF with a large team of dedicated people who are using big data and AI to understand and treat TBI, coma in cardiac arrest, stroke, and epilepsy. So today, Eddie's going to talk about both the opportunities and the pitfalls in his experience with multi-center ICU EEG collaboration. So Eddie, I will stop sharing my screen and turn it over to you.
Thanks, Dick, Ethan, and Craig for the invitation. I'm really looking forward to connect with you, and particularly the Q&A after I go through the slides, because we want to make this interactive and answer questions that people may have about doing this type of studies. So I'm sharing my screen. Let me know if you see a full screen or not.
Yes, we can.
Yeah, it looks good.
All right, very good. So here are my disclosures. I do have funding focus on EEG analysis and that's multi-center studies, but the funding agencies did not participate on the development of this presentation. And before we go to the nuts and bolts, I really wanted to send a thank you to the Physionet team and the collaborators from the eye care consortiums. As you can see here, they are listed, as well as the affiliations of all the different hospitals. So this is really an amazing group of people, and particularly folks in our lab, and Masa, Pravin, and Vishnu, who's joining us today. were instrumental in getting this data set together and getting things ready for the Physionet challenge, as well as some of the grad students at Berkeley. And I also wanted to bring up some of the publications related to this data set that I'm going to go over today. So you have them handy. You have Signal in Red, the one that describes the data, which was published in CCM not too long ago. And finally, if you want to download the data and start playing with that today, right after the session, please, you can reach the database at this link at the Brain Data Science Platform, which is a project ran by Dr. Westover at the Bethtersville Deaconess Medical Center. So all the trained data is available for you to download. So what we'll talk today is like doing multi-center studies using EEG has a lot of challenges. And I'm gonna, instead of just talking about it, I'm gonna talk about our experience running one and running the Physionet challenge, which was led by Dr. Matt Reina and Dr. Gary Clifford and their team at Amorim. So that's a competition that happens every year. And they've done that on EKG, all different types of task, EEG, sleep. And this past year, we ran that on coma post-cardiac arrest and how to predict recovery from it. So we had more than 100 teams from all over the world submit algorithms that would take the EEG data, the continuous EEG data from those patients to predict who's going to recover or not. And it was a really fun experience. Most people participating actually don't have a background on EEG. So bringing EEG to this broader group of folks in computer science engineering was something that was very, very exciting. And I really enjoyed going to Atlanta and get to meet all these people from all over the world that were thinking about coma and cardiac arrest and how to use this data to improve predictions. As you can imagine, running something that's multi-center that involves more than 1,000 patients, many things could go wrong. And we'll go through some of those pitfalls and challenges that we have doing this type of study. So now that I gave a brief intro, I show you the links, I show you where to get the data, what papers to check. You could move on and just go start doing your algorithms and run your code right now, or you could sit through where we're going to walk through the details of the competition. I figure I'll have that front loaded in case people need to refer back and don't have to search through the presentation for where's the link, where's the data, how to find it. So the presentation will be divided in three sections. So first, we'll talk about cardiac arrest in general and why this data means, and that's what motivated us to do that competition. And I'm doing that because viewers might have different kinds of background. They might not be very familiar with cardiac arrest or EEG. I want to make this as accessible as possible to the groups watching. Second, we'll talk a little bit about our experience running algorithms with that data set and what it took to get that in the Physionet challenge and how people went about submitting the algorithms. We have a little demo, so you could just jump on the computer and try to do that yourself. So walk you through about those first steps, and we'll get to run a simple model live. Hopefully the live presentation demo works. It's always a challenge when you're doing that online. And finally, we'll just go over some of the nuts and bolts of running this type of studies, what needs to happen for you to be able to participate, and more practical things. So cardiac arrest is a big deal. We have more than 6 million every year patients having a cardiac arrest. The third cause of death in the US is very expensive. And out of all those patients that have cardiac arrest in the US, more than 500,000, only about 100,000 a year survive the initial code and get to the ICU. But that's 100,000 patients every year. And most of those patients are comatose and have a very complex care that's necessary. And unfortunately, the main cause of poor outcomes in those patients is brain injury. So everybody's very focused on the heart attack and how to get the heart back to work in the beginning. But actually, if you get your heart back to work, is the brain injury that's really the responsible for poor outcomes in the vast majority of patients. So here I have a depiction of a quantitative MRI, and I have a comparison of a normal MRI and quantitative analysis of the diffusion injury. So this patient had a global injury. You see here, the purple indicates severe injury. And that's an MRI that usually happens a few days after the patient have a cardiac arrest. But actually, if you look at the initial CT scan of those patients when they just hit the door in the emergency room, the brain actually often looks pretty good. You can see here the cortex, there's good gray-white differentiation. But over time, you start to develop brain edema. And here we have a CT 3 days after arrest, and we have the MRI 4 days after arrest with really diffuse injury, and this patient had a poor outcome. So is the EEG helpful? So actually this patient, when he had a good CT, he also had a good EEG. And over time, you start to see that the EEG became less complex by day 3, and by day 4, we had primarily a flat EEG, which just tells you that there's a lot of information about the evolution of brain function over time. And perhaps there's opportunities for intervention so we can keep the brain the way it was at 6 hours, where we have good activity, we have a good scan, and avoid the secondary injury that's happening over time as a complication of the initial insult. So I think there's a lot of potential for using EEG as really a real-time monitor of brain function and potentially to guide interventions. And that's why we have been focused on some of the research that we're doing. So this was the motivation to put together the International Cardiac Arrest EEG Consortium. So investigators from UCSF, myself, Yale, ULB in Brussels, University of Twente, Brigham and Women's Hospital, Beth Israel Deaconess, and Mass General all contributed EEG data for 1,020 patients. So we're talking about 57,000 hours of EEG, almost 3 terabytes of EEG data. Those patients did also have some basic baseline information and their long-term outcomes. And we made all that data available to the community through the Physionet Challenge last year. And to walk you through the patient journey here, after you have a cardiac arrest, you get to the ICU, and we tend to place EEG as soon as possible. Not always we get EEG started within 6 hours or 10 hours, but we really try hard to get the EEG started within 24 hours because there is a dynamic evolution of the EEG, like I showed you on the previous case. And we tend to monitor patients for different durations. Usually it's through the hypothermia or TTM phase or normothermia these days and in some centers. And we do that, we rewarm the patients, and we want to watch as they wake up because they may have seizures. Also, the background can give us an idea of, is this patient getting better or not? What is potential of recovery? So if you have an EEG that's continuous, that has good frequency content, that's an indicative of having a higher chance of having a good outcome. So we want to monitor for that. And there's also deterioration. So here we have an example of a patient I took care of where we have the raw EEG with someone with a flat EEG because the EEG was started very early. And you can see over time, he developed burst suppression, which is this flat followed by a burst of activity type of pattern within the first 24 hours. And little by little, by day 2, the EEG was more improved. And by day 3, the patient woke up. And you can see here on the spectrogram in the top that the patient was on burst suppression initially. So you see way more blue on the background of the spectra. But over time, you start to see more red and green, which indicate a higher power, a higher amplitude of the EEG. And the higher it goes on the y-axis, the higher is the frequency content of that EEG activity. So you can see how the evolution of data, how the longitudinal changes on the EEG can really help you understand what patients might do better or not. The other thing that's important when you look at EEG on those patients is to think about patterns. So if I just mentioned to you, this patient had a flat and a burst type of EEG, so it's called burst suppression. And later, the EEG became better, had more complexity, more frequency. So that was an EEG that had more entropy. So this is the data set, the iCare data set. And we did a Disney map. So it's an unsupervised method. In the distance between each of those dots is how different the EEGs are. And we are looking here at thousands and thousands of snapshots of EEGs. And you can see here that they're clusters. So they're different EEG patterns. So we color in blue the patients that had burst suppression. We color in green and yellow patients that have spikes or seizures. And you can see here that also, if you had spikes that have higher entropy associated with them, so there's a background in between the spikes, those patients have a much higher chance of having a good outcome, 19%, versus patients that have a flat plus spike background. So that's just to tell you that individual snapshots and the evolution of EEG data can help you better understand who are the patients that are more likely to recover from a coma or not. And that was really the impetus of the challenge. Here's when we break down by the CPC score, which is a scale that measures the recovery of the patient. So a CPC of 5 means that the patient is dead. A CPC of 1 and 2 are patients that are independent. And a patients with CPC of 3, they have severe disability, and patients with CPC of 4, they have UWS, unresponsive wakefulness syndrome, or what we used to call vegetative state. And you can see here that depending on the group, you might have a very different trajectory of evolution of EEG features. In this example here, we're highlighting spikes. So at 6 hours, all groups had a very similar spike rate. That's what we have here on the y-axis. But over time, all groups had some spikes come, right? And this is a group average. But you can see here that the slope of that curve was very different based on the outcome. So patients who died or had a severe disability, they tend to have more spikes than patients that had a poor outcome, even though both had increase on the spike rate. And this is something that we see on different type of features, like burst suppression, when you calculate the degree of flatness on the EEG, or the complexity of the EEG signal with entropy. Those three features tend to have different signatures over time in terms of their evolution, and they have good separation between the groups over time. Some other features, they may actually not separate very well early on, they may separate better, or they may separate early but not later. And that's why we tend to look at several domains of information when we look at the EEG signal and decompose that in features. And that's the more traditional way of doing EEG analysis and signal processing. But the new methods of machine learning, and in this case, convolutional neural networks, we are actually getting those snapshots of data and acquiring features in a different way. So just think about it. If you're trying to build an algorithm that's going to separate pictures of cats and dogs, we did the same for EEG data. So the convolutional neural network would scan the pictures and learn what's most important features within each feature from all the patients to identify what might be more salient and more relevant on that task of predicting who is going to wake up from a coma. So that's a study that Dr. Wei Long, myself, and Dr. Restover, plus the ICARE group put together a couple of years ago, where we took the information from the CNNs and we started to classify the EEG. And we fed that information to a long short-term memory network. So this is a convolutional neural network. So it will take into consideration the evolution of the features of each of those snapshots. And then we try to find out who is going to wake up based on that. Here we have some of those initial results. So the algorithm performed well, and the best performance was achieved at hour 66 and after cardiac arrest. And you can see here that the gray line, which only had data up to 12 hours, had the worst performance, but which is actually not bad. So even with a few hours of EEG alone, we had a UC of 0.83. But as the algorithm got more information, more data over time, the algorithm kept getting better and had better calibration. So whenever it predicts that's going to have one type of outcome, that really tend to match much better. And that's something that improved over time. We also have here the summary of that algorithm compared to many other deep learning methods and more vanilla type of machine learning things like random forests. And you can see here that the red line, which is the algorithm that has a combination of CNNs and LSTMs, performed well, but it did much better over time, which was also the case of many of the other methods, which included TCNs, BLSTMs, they're unidirectional. This was a bidirectional one, the red line that did best. But just to show there was consistent, the more data led to better predictions. And interestingly, we want to bring that back to individual patients when we build those algorithms. So these algorithms allow us to pick one patient and then try to see based on that patient what the predictions are. So you have here 2 examples, a patient with a good outcome, so a CPC of 1. You can see that the chance of poor outcome based on the initial EEG at 12 hours was pretty low at 16%. And that stayed pretty stable over time. Even though the EEG got better, right? You start to see more frequency, more waves by 60 hours. On this patient who survived but had severe disability, the EEG was pretty flat early on. So the prediction of poor outcome was already 64% based on just few hours. But as the EEG evolved into spikes and then seizures, and you can see the spectra and the waveform changes over time, the confidence on the prediction of poor outcome went up from 64 all the way to 84%. So that's just to represent that those fancy algorithms can also get back to the individual patient level prediction. So we thought that, our methods were doing pretty well, but can we do better? Are there different techniques that we're not thinking about that could improve predictions? And that's why what motivated us to open the data, let other people develop that type of algorithms, come up with new ideas. They'll help the field move forward faster. So let's talk about sharing the data with the world and how that went. So I think right now we all understood, I hope you understood, that cardiac arrest is a big deal, that brain monitoring cardiac arrest is important, that the evolution of the data and the content of the data is really relevant to understand who is going to recover or not. And there are some pretty good algorithms out there that could ingest this massive amount of data to build prediction models. This image here, this table that I have, is just to give you a comparison of the previous, more recent Physionet challenges, which is a competition that happens on the cardiology conference, computing cardiology conference every year. And the data set that we have from the ICare, which is highlighted in blue here, involved EEG, involved 1,000 patients. So that's way less patients, right? When you look at the arrhythmia detection, we're talking about more than 100,000 people. But when you look at the amount of data that we had for those 1,000 patients, is really massive. So we're talking about more than 60 billion data points, more than 1,000 hours of EEG, and almost 3 terabytes of data. And we'll talk about some of the challenges of pushing so much data up and getting people with their laptops all over the world to download things locally, how that was not so straightforward for some. But it was a really fun exercise and we learned a lot from doing it. So this is to give you some numbers. I'm not going to focus on the specific numbers, but we had almost 1,000 submissions. So people put together algorithms and they submitted that to us, and we'll run that model to see how well that's working. And we'll talk to you what's the process for that. And a lot of the submissions didn't work because the code didn't run. And that's another important thing whenever we build code, particularly code that's going to be usable by other people, which I think is a very important problem. You can see here that almost half of the submissions didn't work because the code didn't run. So this challenge, there's a very organized way, and I'm going to show you some of the code for that the submissions have to be organized so other people can run it. And if you submit code that doesn't run, we'll just let you know, I'm sorry, we couldn't run your code, please fix it. And there's helper functions. There's a suite of things that was put together by Dr. Clifford's lab and Matt Reyna leading the effort that really have made this a much more smooth challenge to run. So I was very impressed by that. And I think we learned a lot about how to organize our code from participating. You can see here that most people were submitting in Python and not MATLAB. So you can see that in red. And people had both CPU and GPU. So we had some very simple algorithms relatively, and we had some really fancy state-of-the-art deep learning methods. And not necessarily the very fancy deep learning methods work better than the more conventional approaches, which I think is very telling about how there are many ways to solve a problem. And this slide is just a little bit of a fun slide where people always wait for the last minute to submit. So you can see here the number of submissions on the x-axis and the y-axis, we have time. And we have a initial phase where people are just trying things out on as part of the data set. And then the challenge has a second phase, which is the official phase, where people are submitting things in the cloud. They're having a more robust method of checking things. And so that was interesting because people are really waiting for the last week or two for the more responsible to submit their code. And you can see here that a lot of this code didn't work. So the earlier you submit, you tend to do much better, both in the code working and also in performance. So that was something that was encouraged. Try to submit your code as often as you can, because that will help you get better results. So this was a little bit of an overview of what the challenge was, how big the data set is, what people are doing with the algorithm. So let me walk you through the details, right? So first of all, we have 7 hospitals from Europe and the US. Each hospital has a different type of device that records EEGs from patients, right? And that's what we have here in this figure. The yellow section is like all the things that need to happen at the hospital level to get this data out. And the BDSP, the Brain Data Science Platform, is the cloud where people are submitting this data to. And we did some processing on that. And finally, we make that available to the public cloud where people from all over the world could download their data. To keep that in perspective, so each hospital has a different type of device often, and the data is going to be on the proprietary format of each device. So what we asked was for people to convert that data in European data format was the preferred file type for that. EDF Plus has some advantages and is more commonly used these days for that, where you can actually not have issues with gaps on the recording. So that's what we asked each site to do, and they did that independently. We supported that because some centers do not have people that are familiar with programming. So it's hard to do this one file at a time manually in the GUI from the software. So we helped them with code and getting APIs from each software company to run that locally so they could get the data de-identified and converted to EDF. So once the data was shared to us, and there are different methods for data sharing, most from STP in the data and sending that through the web. And we then start to harmonize the data. As you can imagine, people name different channels, different things, and getting that all harmonized was important. One important piece is like people have different reference LHOs on their recordings because they have different styles of recording. So we had to know what the reference was, and we had to re-reference the data into bipolar or an average montage. There are a lot of channels that are recorded that don't have usable data, so they're not plugged to the patient. So we had to figure out what channels you're actually using or not in your shop. They're actually doing your recordings to organize that. So those are all back and forth things that we had to do with each site that I think would be very important if you're thinking about a multi-center study, is like what format you're going to be, how you're going to get the data, but also once you get the data, how to wrangle all those different things. After that, we have de-identified data, the channels are harmonized. We then decide to convert from EDF Plus to WFDB format, and I'm going to walk you through what the WFDB format is in more detail. So whenever you go to the web and you download the data, you can actually understand how to run it. And we did that because that separates the header information that has, for example, the sample frequency of the recording, when the recording started and ended. And we also allow us to put together the signal data as a separate file, so you can load them independently. And it's a very fast type of format, and that's widely used on the signal processing community. So people who participate in the Physionet challenge would be very familiar with the WFDB, which was something that me as a person working with EEG primarily haven't really spent that much time working with. So that was another thing that we learned from participating on the competition. One caveat before I walk you through the specifics of the data is that we made all this data available, but you cannot download the data from all the 1,000 patients. And why did we do that? So we made the training set available, so 607 patients, and you can train your model, build your model based on that. In the challenge, you can then submit your algorithm, and we'll run your algorithm against the validation data set, and you'll give you back the results. So how well your model worked. And we did that so people can get feedback on their model performance on a set that they cannot manipulate. So even if you're not trying, sometimes by mistake, there's some leakage across your training and testing set. And people tend to build models that will work well on the test set, and they iterate from that. So that's like an unwanted outcome of doing that type of training, testing, splits. So what we did is to make this validation set so you can do the training and testing, but you're not manipulating your training based on that. And then we had a full set of 306 patients that nobody saw at all during the entire challenge preparation. So the challenge started in March and went all the way to the fall. So people could submit code, test your algorithms, do all those things way ahead of time. But we didn't want to make the test data available, and we wanted to save that until the very end so people could really see how well the model was performing on this bigger data set. And we kept an entire hospital data on this test data set, so we could see how the models performed on a different hospital than the hospital that the data was trained on, because the trained data set had data from 6 different institutions. To go back and explain you what the channels, some of you might not be familiar with EEG, so I just figured I would explain. So there are many different channels in the head. They're organized with odd channels are on left and even channels are on right. For this competition, we had 19 channels. So in this image here, I have way more channels than that displayed. And here's what I'm highlighting. So just to give you an idea of how things are organized. So we have here left, right, right, and the midline electrodes with the temporal chain representing red, the right temporal chain representing red in yellow. And you can get how that is displayed in the head. And just to give you a sense of what is in there, because when you actually, if you're going to download the data, that's what you're going to see. You're not going to see this pretty display. You're not going to be too familiar with how things are organized if you're not working with EEG already. And here is like all the different channels that were used. The focus was on EEG, but actually we also made the EKG data available. Not every patient had EKG data available, but most of them had. And actually some of the people participating in the contest, they included EKG variability metrics into their models. So their models were trained on both EEG and EKG data. There are also eye electrodes like LAT, LOC, ROC. So there's some additional electrodes that were available. And there are also the references electrodes. So we had everything organized. So here is actually what the header of the file looks like. And I'm just spending time to walk you through because I think this could be a good reference for folks that are interested in doing the analysis and run your own algorithms. There are multiple math files. And in these files, we have the different channels. You see here, FP1, FP2, O1, O2. And there's a bunch of different numbers, which I'm going to walk you through very quickly in a second. And we have here both EEG and EKG files for some patients. To walk you through quickly, and I'm not expecting you to focus or understand all the details, but I just wanted to make this available because for those who are watching who want to understand this better, you have the instructions available in the video. You can just hit pause and get through all the explanations. So the way the file is organized, we have the patient ID. We have the first EEG for the patient. This is hour 2 after cardiac arrest. This is an EEG file. There are 19 channels. The sampling rate is 500, and this is the number of samples on the file. Then you get on the really detailed numbers, which I'm not going to get into through, but this is a math format file. We have a checksum of the files because we want to make sure the file you downloaded from the cloud wasn't corrupted in that process. So that's something that's really important when you're working on this type of data set, to make sure that when you're downloading thousands and thousands of files, there are no issues with that information coming down. So we made that available as well, so you can compare what it should be with what you have. And we also have the start and the file, the utility frequency of each file available. In addition to each individual level file, we also included the clinical information that was available for that patient. So you have a shockable pattern on rhythm on your EKG when your heart stopped. Are you female? How old is the patient? What's the outcome? So that's what you're going to read to train your model. And then we have the scale of outcomes that I explained to you before. It goes from 1 to 5, with 5 being the worst and 1 being the best. And the way the competition worked was actually, we wanted to build a model that has the best sensitivity at a false positive rate of 5% or less. So when you're predicting poor outcome, you don't want to predict that the patient is going to do badly and the patient actually wakes up, right? That would be a very dangerous thing to do. So all the prediction models in cardiac arrest, the majority of them at least are, and when it comes to prognostication, are very focused on the false positive rate. So you want to have a false positive rate of 0 if you can. The problem is, like, when you have a false positive rate of 0, your sensitivities tend to be very poor in many of the models and things available out there. So that's why we had some wiggle room on that, particularly because there are a lot of limitations on this data set, right? There's a withdrawal of life support that's often happens before someone dies. So people think that the injury is very severe and they would not want to continue life support. Then life support stopped. And that could be that person most of the time, near 100% of the time, after you turn off life support, that person will die. So there is some bias that could come in, be baked into the data because of those practices, right? Because it could have, for example, a good-looking EEG, a good-looking brain, but you have really bad heart failure, and you don't want to have mechanical support for your heart. Therefore, that person will end up passing. So even though the EEG, the brain was good, the heart was bad. But when you're building the model here, you're training on the EEG data. You don't have all this contextual information available. And that's why it's important to keep that in mind, that all those methods we're talking about in algorithm, they're not perfect. And that's why, keeping that in mind, we kept the 5% false positive rate or less as one of the metrics. So whenever tuning the model, people wanted to maximize this metric, right? Which was the maximum sensitivity at a 5% or less false positive rate. And we're expecting to see, as an output of the model, was to a prediction of good or poor outcome, which is what we're showing here. And we're doing that at the individual patient level. So for patient 284, the algorithm predicted good outcome. The outcome probability, and that's a poor outcome probability, was 19.5. And we also asked the teams to predict what's the CPC score between 1 and 5. In this patient, the model predicted a CPC of 1.5. So those are some of the things we did and how the competition was organized. So to recap, I went through all the important things about cardiac arrest and how EEG evolution is important. We went through some algorithm examples and how the challenge was set up. And now I want to give a little bit of a demo of, if you would want to download the data, what would you do? So I'll stop sharing for a second, and I will share my desktop here. So first, I'll start with the website where you would need to go to download the data. So that's the Brain Data Science platform here, so bdsp.io. And you would click on data. And here, there are all different types of data sets you can download, actually. So if you're interested in EEG, burst suppression, there's a lot that Dr. Westover's group and Dr. Mora and his team, plus a lot of great people out there, put together. But today, we're going to look at the eye care. So here on the databases. So here we have all the authors who participated on the eye care consortium setup. We have here the citation, so you can put that on your paper if you're doing analysis and you want to publish. And then we will explain a lot of the things we talked about today here. And if you scroll all the way to the bottom, you can actually get a specific path to get you the data. So you have to create an account in BDSP, and this data is stored on Amazon. So you would pull that from Amazon to go to your terminal to get that set up. So that's something you could do today, so you don't have to wait for that. The other website that I want to show is the GitHub. So in this page, here, there's all the explanation about how to get, once you download the data, how actually to run the model. And there's very detailed explanation Dr. Reina, Dr. Clifford, and their group put together here. And I wanted to do this way because I thought it would be really important to actually show you that this is not complicated, not a complicated thing to do. So here is how the data, once you download, is going to be organized in the different folders. I only got two patients here because we want to run the model with you live. So this is what the data looks like for two patients. You have the ECG here, the EEG, you have all the data information, all the header for each file that explains everything, the text file that has the clinical information about that patient, how old they are, all that, everything is here. Okay. And that's how the folder is organized. So let's say you're going to go download this, you're going to have that locally. So the first thing you need to do is to set up a Docker. And for those not familiar with that, Docker is a type of app that will basically save all the information of your setup for running something, and it could be anything, in one place, because it's always a problem when you're setting up your code that there's a lot of dependencies. So Docker kind of helps, and there are different apps that do that. In this case, Docker was used. So I have Docker running here, so you have to turn that on. And then I have here my terminal, which has all the, where we're going to enter all this information here. I'm going to minimize that, put that to the side here. I already ran this earlier today just to make sure that things were working properly. So some of the things we'll go through are not going to, may already be downloaded. So you'll see that when I run it. So the first thing we want to do is to build the Docker image. So I'm going to copy that here. You can see that command on the Physionet page here. So after you download, you have the directories, all those folders I showed you today with the training data. You want to make sure that you have your computer path here, so it knows where to do the data. You want to download this repository here. You want to clone that locally. So all this code is in there. And then finally, you want to get your Docker set up. So that's the 0.4 here. So I'm going to put that. Okay. And let me open a new terminal just in case. And that's whenever you do a live demo, you can always run into some of those issues. So I'm going to CD to that folder. So we are on the right place. And now I'm going to run the Docker command. And if that doesn't work, I have some snapshots of this. So I can just show you where things would be. Okay, so you can see here that everything was downloaded. As you can see on the previous terminal, there's way more things in there. And there's an error on the Docker. Okay, all right. So let's switch gears here and go back to the PowerPoint. By testing it this morning, maybe I had something broken. And I just walk you through what the outputs will be. In 1 second. Okay, as I told you, here we have the Physionet page. And here we have the file folder. And here's the code, the build Docker image. Here is what the results of that would be when you have your Docker set up. And what you should do, as you can see here in the bottom, we're just going to run the command to run the model. And once you do that, you will get the result, and that's what the result would be. So for example, for patient 398, the prediction was poor, the probability was 0.74, and the CPC predicted was a CPC of 4. As I mentioned, this is a built-in test code. So actually you don't have to run that code. That's a code that's already built in by the Physionet team. So whenever you download the data, you can make sure that the code is working, and then you would just update your code. So to show that to you, so the way the code is set up, you have a train code that's written by the Physionet team, and there's a team code, which is what your model would be. So people would modify this based on whatever they want to do. If they want to do a deep learning model, if they want to do a random forest model. What this does is to train the model and predict the CPCs based on the features in the model details. Here's the training part. So in this case, they have a default random forest. You have the number of estimators, the nodes, the random states, where to see that this is going to start. So this is all already available. And here is like the code to training the random forest. This code also already includes some features, right? So in this case, here, we are acquiring EEG features. So here in the bottom, we have the extract features part, where we go through the different channels. In this case, you look at the bipolar channels, and we are getting 2 features. I think we had the suppression feature and some band power features on the test code. So the nice thing about this is that we already provide you code that's running that you can test locally to make sure that all the different parts of the setup are working. And that is, I think, really helpful. You just have to update how you want to extract features, what type of model you want to try, and that would be all that you need to get yourself going. So the good thing about that is like you don't need to be super advanced on EEG analysis or model development. You already have something to start working with, and then you can just build on that. So I'm going to go back to the PowerPoint and share that with you. So this is the result of the algorithm. So what could go wrong? So I think we went through cardiac arrest EEG models, how the data is set up for the competition, how you can just go at home now and start working with this data and do prediction models on that. But there are other things about putting this type of data set together that we didn't discuss that I think is something that I want to open up to the group. So as I mentioned before, there's confounders on the data, right? Use of sedation as a problem. There's a withdrawal of life support. There are different types of data conversion. There are many different hospitals. There's a lot of artifacts on this data set. That's something you didn't go into detail, but there's a lot of times that the EEG is not connected to the patient because the patient went to a CT scan and you still have the machine running. So this is like real world noisy data that you're going to be built on. So you might want to use some artifact detection method to make sure that you don't have garbage in, garbage out on the models you're developing. Getting this data on GCP was easy, but not everybody was too familiar with the Google Cloud platform, which is where the data was for the Physionet challenge. Now we have an AWS. So there's a lot of troubleshooting that had to happen because of that. And I think the code that I showed to you and the setup that I showed to you was really helpful, instrumental in getting people from all these different places across the world with different levels of expertise to get this up and running. As you saw, more than near half of the code that people submitted didn't work. And so I think this rigor on having the code running and being very careful about that, so you have a robust output, was a really important feature of the challenge and something that we really thought was important. So to close up, we have the Brain Data Science platform is what the data is. So please go there, download the data, and start playing with it. I'll be happy to take questions. Thank you.
Thank you, Eddie. That was wonderful. So if those who are attending can put your questions in the Q&A tab, we will start answering those. And Eddie, I think you have access to that, right? The Q&A tab. So when we
Yes, I can see that here.
I'll start with a question if that's okay. I see a lot of commonalities between the stuff you did for data conversion, data anonymization, and sending to the cloud with some of the stuff we're doing. Can you comment on any of the limitations with, the number of copies of data you've made? Because if you transfer data, you create a copy of it, then you anonymize it, then you upload, then you download it, that's 5-6 copies of it. And I'm wondering if there's anything that can be improved going forward to limit the number of times you have to copy the data to not explode the data storage requirements, you'd have to do something like this.
No, absolutely. And I mean, it's not trivial, right? We're talking about 3 terabytes of data. While that might not be too much data for some people, if you have like your computer and you're trying to do those things, that can be complicated. And in the cloud can get expensive. So I think the caveat here is like this was a long project, right? So when we start this project, we're not thinking about, oh, let's make sure that we share this data with the world. Let's do a competition so everybody can build algorithms. So that was something that we were not thinking about back in 2017 when we got started. So if we would do this again, we'll probably have an agreement of what's going to be the final format to begin with, and do all that conversion and changes at the very first step. So whenever we're building the pipeline to convert things, we would just add that on. So there is a single final de-identified version of the data set. It's already harmonized. The problem is like you need data to figure things out, right? And that's something we are facing now. We are part of this project called the PORS project, a Bridge to AI NIH-funded project where we have data from 14 different hospitals. We can talk about what the data looks like as much as we can, and each site can talk about what the data looks like as much as they can, but we only really know how hard things are going to be when we actually get all the data, at least sample of the data together, because we're going to find all those issues that people didn't think about because they didn't have access, and people have different types of expertise, so they may actually notice and identify issues that you didn't think about. So that's kind of the hard thing. It would be nice to agree from the very beginning and you do a single conversion, but that was a limitation. And I think the other problem is like the EDF is kind of the standard type of file, and a lot of the other algorithms that we have and other labs have are expecting to start with an EDF file, not a WFDB file. So sometimes it's easier to have things on EDF depending on your pipelines that you're using. So that has been something that we've done. That we need to keep in mind. And depending on the type of file, like EDF versus WFDB, they have different compression rates, right? So then actually the hard drive space might be very different depending on how you're compressing your data. So that's another thing to think about. We chunked the data into less than 1 hour segments for the competition, so people can load things faster, you can parallelize things faster. And that's not often the standard on how those files get downloaded, right? Each patient is like 24 hours of EEG, and that can be several gigabytes per file, which is a problem when you're trying to load that to memory in some of the setups we have. And sometimes you need to load the whole file. You cannot load chunks of files like you can do with HDF5 kind of formats, for example. So I think there are a lot of like nitty-gritty details about data loading and data processing that you raise are really, really important to avoid the issue of having multiple copies, because the more copies you have, the more prone to issues and difficulty and reproducibility you're going to have. So I think those are all common issues that we're all learning more about now that we're doing studies with like 7 hospitals, 14 hospitals, which I think is going to be really important to get the algorithms that we have deployed in a generalizable way.
Most definitely. I'm excited to see what comes next for the Bridge to AI project as you take the lessons learned from this Physionet challenge to that. We have a question from Baptiste. This is a great and impressive talk. What kind of cloud are you using? Is it one from your institution? And how did you manage to build this impressive collaborative project with notice on financial resources, authorization, and things like that?
Yeah, absolutely. So this is stored on AWS because this data is open to the public and people can download and do research with that. That's being supported by AWS. So AWS has an initiative for this open data access that Dr. Westover was able to arrange. So there's not charged to keep the data there in terms of keeping terabytes and terabytes of data requires a lot of costs. So I think that's certainly something that's very important. It's another thing we're discussing, talking about the course project. That's going to be really important. And the data has to be open for that to be the case, right? So it takes time for you to get the data to the open phase. And you still have costs to keep the data, to do all the cleaning and all those different steps. So you need to have resources, and we are grateful from support from the NIH and other foundations, the Neurocritical Care Society, the American Heart Association, the Society of Critical Care Medicine. They all contributed to funding to the investigators that were participating on this initiative. So there's certainly a lot of costs that are related to getting the data and having the engineering time to do it, or the physician time, like myself and others, to be engaged on that. So we are very thankful for the support for that. The other thing I didn't talk about was the agreements and paperwork, right? You need to have data user agreements between the institutions. And when you have European institutions, that has to be compliant with GDPR. So that's another type of agreement that you need to have so you can actually receive the data. And I think the de-identification of the data is really important because that's really de-risks the sharing of the data. So having a pipeline that would de-identify the data well without risk of PHI sneaking in was important. That's much easier with EEG data, right? Because we have a bunch of waves, and that's the most important thing we care about. The header is just a few fields that tend to be pretty standard, so it's easy to de-identify that. It's much more complicated when you have images, when you have burned-in pixels on images. So depending on the type of collaboration, the de-identification aspect can be a challenge. And each institution has different bars and IRBs in terms of what de-identification level is necessary.
Wonderful. Do you have time for one more question?
Yes.
So we got one from George. Thanks for the high-level overview. Was there a winner selected in the challenge? Were algorithms tested locally, or is the data so large that cloud computing was necessary and performed? And what advice would you have for starting a similar project with image data?
Absolutely. So a lot of things packed in there. So the first thing, yes, there was a winner. There was a cash prize for that. That was from the Mass General group. Dr. Eric Rosenthal's lab, Morteza, was the leading author on that, but it was a group effort. So their team ended up winning the competition. As far as first place, there are like prizes for second place, third place as well. And the algorithms actually work better than ours, which is something that we were pleased to see, because that's the whole point of doing this. And the model that was winner, they also did some feature importance analysis on it. And so you could try to understand what type of EEG features were more relevant and the predictions, which is something that I was pretty happy to see. So it was not like a complete black box model. So trust me, the code works, even though it didn't work in the call today as we did 2 hours ago, but things worked pretty well from the competition. In terms of the algorithms tested locally, so you can do whatever you want locally, and you can use GCP that was made available to the people participating in the competition at a time. So they could run big models if they needed to. There's some limits on how big the model is and how long you can leave it running in the cloud, because that can get expensive. But there was support from partners for the challenge and their list. And so I think we're very thankful also to them to have made that possible. So yeah, so to answer that, cloud computing was done. Some of the models they were tested. They were tested in the cloud as well, but some of them were actually pretty simple models that you could just do on a laptop. So that's just a reminder that you don't need to have all the super expensive resources of cloud computing to start working on this data set. So you can use much more simple things. And what other advice would you have for starting a similar project by using imaging data? So as I was referring to the data agreements and the de-identification, I think those are like key things that have to be figured out. And there's no clear solution or champion solution out there that I know of on doing that. There's some pretty good solutions that work well for 99% of the images in terms of de-identification. But they're never, I haven't seen one that's 100% foolproof. And often there's a team of engineers that are necessary to support that de-identification effort. And that has to be partnership with physicians, because you're going to have to go check on the data to see if there's no PHI that was leaked. And to me, that's one of the biggest barriers of doing something like this elsewhere, is just how the de-identification is going to happen. So once the data is de-identified, I think then we are off to the races. There's a structure that the Physionet group has set up. I think it has been really robust to test the models that the different teams have. So I'm very thankful for the Amorim group for putting that together. And that's something I think we want to emulate going forward in different code sharing efforts, as well as future competitions. Dr. Westover, for example, has a competition going on right now also for seizure and bad EEG, epileptiform EEG prediction. So I think we will start to see more and more of that. And I think that's a very appealing way for those NIH-funded projects, is you're not just making the data available, but you're getting people from all over the world to contribute to making the models and the research better. So you make the data sharing also an opportunity to improve and algorithms and move the field forward.
All right, any final questions? And it doesn't look like it. So Eddie, thank you so much for doing this. Thanks for taking your time, morning your time. And thank you, Baptiste from France, for tuning in. And we have a hardcore of European listeners. We really appreciate that. And thanks to all of our other participants. And please send us your comments. And if you'd like to do one of these webinars with us, please let us know. So thanks, everybody, and we'll see you next month.
Thank you, Eddie.
Thanks, Eddie.
Thanks, everyone, for joining.